Alright, so this is Lab 4, Circuits and Capacitors, by me, Nikita Crisp, for Physics 2212P, for Dr. Wise, and for this lab we used an online circuit construction kit, or CDCK, from the Colorado PhET project. So for this lab, the purpose was for us to use our knowledge of energy and current conservation in order to predict the behavior of circuits containing resistors, both in series and parallel. We were also supposed to use multimeters in order to measure the values of conventional current and the potential differences in the currents. We also used voltmeters to measure voltage as well. And finally, we were to examine the behavior of ohmic resistors and capacitors. And within this lab as well, you will see the concepts of the node rule and the loop rule being used. So some assumptions for this lab. So what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuits you hooked it up to? So if done in real life, the current measured by the ammeter would be lower since a real ammeter has resistance, whereas the ideal one showed in this model does not. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So if done with a real battery and a capacitor and no resistor, then the capacitor would take up a longer period to reach a full charge than that in our idealized model. This is because all circuit components have some resistance in reality. So for my data here, you can see that with my voltmeter, in order to prove the loop rule, I took the voltage or the difference in voltage between A to B, B to C, C to D, D to E, E to F, F to G, G to H, and H to A in the circuit. And you can see those differences listed to the right. You'll also notice that the sum of all of these voltages add up to 0, which further proves the loop rule that any closed circuit will add up to 0 in voltage. So for some more data here, this graph further proves the loop rule in that the overall difference in voltage of the loop was 0. And you can see the different spikes and dips as you add on either a positive voltage or subtract with a negative voltage. And you can see where that corresponds to in the actual circuit on this graph here. Also, when measuring between different ohm levels in light bulbs, we saw that in the 10 ohm bulb, the capacitor took 2.5 seconds to charge, and it took 4.28 seconds to discharge, and with the 20 ohm bulb, the capacitor took 4.41 seconds to charge and 8.32 seconds to discharge. So this shows us that when you're doubling the resistance in a bulb, you would also double the time it would take for a capacitor to both charge and discharge. And we can also see that discharging takes twice as long as charging capacitors. So here graphed is the data taken when the capacitor was discharging. You can see in the table to the right, in the left-hand column is the timestamps taken. They were taken for 20 seconds total at 2-second intervals. You can see the voltage decreasing at an exponential rate, which is why we've graphed it on a logarithmic scale in order to get a nice clean line with a clean slope. And the slope is negative 0.1666, which, if you do the math, becomes an RC value of 6. And this does agree with the RC value of the circuit in the CCK.